What's up guys, Mrs. Thompson here, and today we're going to cover solubility curves. These are graphs that you'll need to be able to interpret. Alright, so here's a typical solubility curve. Here's the solubility of salt and sugar in water. And so what's done to make this solubility curve is you take salt and sugar and see how many grams you can fit at different temperatures, and then you produce a graph. Sometimes it makes just a straight line, sometimes it makes a curve like sugar. Alright, so here we go. It says solubility curves are made by determining the mass of solute that will dissolve in 100 grams of water at several temperatures. And so on this graph, what you see is 100 milliliters of water. That's because 100 milliliters of water is the same thing as 100 grams of water, because the density of water is 1. Alright, then that data is plotted on a graph, just like that one. And for this graph, what you see is that each little line on the graph is a different substance. So you have a bunch of things on one. So you've got sugar and salt on this one. You could have a whole bunch of others on the same graph. And so that line is just specific to sugar. This line is specific to salt. Okay, so why do we need these graphs? So it says we use solubility curves and the plot of new data to determine if the solution is one of these three things: saturated, unsaturated, or supersaturated. Remember that saturated is when you have the maximum amount of solute that can dissolve. Unsaturated is when you have less than maximum, and supersaturated is when you have more than maximum dissolved in there. Alright, so this graph, make sure you have one of these, so make sure you add solubility and temperature. Now on the dashed line, that's going to represent a substance. That's where it's saturated, because that's the amount that can be dissolved at that temperature. So if we look at a temperature and grams on the graph and we find that it's on the line, we can say that that solution is saturated. If it's unsaturated, then it's going to have less than the amount that it would need to be saturated. So the plot would be below the line. Supersaturated, well, that's going to have more dissolved than it can usually dissolve, and so that's going to be above the line. So let's label that on the graph. So unsaturated would be this pink region here, and supersaturated would be the blue. Alright. Or we can use it to determine the mass of a substance that can dissolve in 100 grams of water at a certain temperature. So if I needed to know, okay, I'm going to make a saturated solution of sugar water at 20 degrees Celsius. So at 20 degrees Celsius, I can fit 200 grams of sugar in every 100 milliliters or 100 grams of water. Okay, I'd like you to try it. So if I was looking at this graph and I had the temperature at 30 degrees, how many grams of sugar could I dissolve in 100 grams of water? Okay, so you do that, read where 30 is. Maybe draw a line or just draw your finger up to where that curve meets the 30-degree temperature. And then read over to the side and estimate, say it's about 220 grams. Alright, so then the other things that you can do is you can determine which substance on the graph is the least soluble and which substance is the most soluble. Alright, so here we've got a bunch of different solutions, solutes dissolved in water. We have A, B, C, and D. We don't know the identity of them. We can tell that which ones are the most soluble because they would have more grams dissolved. So A would be the most soluble in this set. And then the one that would have the least amount of grams dissolved at that temperature would be the one at the bottom. So that would be the least right there. Make sure you draw that on your graph. And then it says, recall that gases are more soluble at lower temperatures. Remember that as you add energy to gases, they escape. And so what you see from gases is you actually don't see a curve upwards like you do for solids. What we see is a slope downwards. So if I had to pick which one of these, A, B, C, or D, is a gas, which one would you say? Hopefully you said that one, because it's the one that actually slopes downwards. As you increase the temperature, its solubility goes down because those gas particles escape. Alright, so we're going to do a whole bunch of examples. Here we go. So here's my solubility curve. It says at 20 degrees, how many grams of potassium nitrate can be dissolved in 100 grams of water? So I'm going to find potassium nitrate. Remember, potassium is K. Nitrate's NO3, so we're looking for KNO3. That's right here. So that means this entire curve is for potassium nitrate. We want 20 degrees. So 20 degrees is right here. Where it meets the potassium nitrate line is right there. So we'll read the grams off to the left. That's 20. So 20 grams of potassium nitrate can fit in 100 grams of water at 20 degrees. Pretty easy. Number 2, at 60 degrees, how many grams of potassium nitrate can be dissolved in 200 grams of water? So slightly different. We'll do the same thing. We'll go 60 degrees. Where does it meet that potassium nitrate line? About right there. Read over to the left. So about 90 grams can fit. Okay, so that's 90 grams of potassium nitrate can fit in 100 grams of water. The question doesn't ask for 100 grams of water. It asks for 200 grams. Now you can logically figure this one out pretty easily. You can say, okay, if 90 fit in 100 grams, if we have double the amount of water, 200 grams of water, then we're going to have double the amount of potassium nitrate. That's going to be 180 grams. It's not always nice and neat like this, though, so I'm going to show you a process for figuring this out. So if it's an uneven number, like how about 238 grams of water? How do you figure that out? Well, what we're going to do is use a proportion. So if we know that 90 will fit in 100, then x, which is what we don't know, will fit in 200. Okay, so how do you treat the proportion? You cross multiply, get 100x is equal to 200 times 90, and then divide both sides by 100. And my answer becomes 180 grams of potassium nitrate. Okay, now the proportion is not necessary when you have something easy like this, 200 grams, but it is necessary when you are doing something that's an odd number, strange number. All right. Next question. Which substance is the least soluble at 20 degrees Celsius? Okay, so we're going to find 20 degrees Celsius. The one that's least soluble will be the one on the bottom because it's got the least amount of grams. Because as you go up, okay, like this one, it's 8 grams of potassium chlorate. And then this one, that's the next one, that's about 20 grams of potassium nitrate. So if you keep going up, we're just going to increase in the amount of grams that can fit. So the one that has the least amount of grams would be the potassium chlorate. It's the least soluble. All right, number 4, which compound is likely to be a gas and why? So in the beginning, I told you that gases decrease in solubility as temperature increases, And so which one decreases in solubility as temperature increases? The one that slopes downwards. So which one does that? This one right here. Ammonia. Okay, and we'll write that. The solubility is decreasing as the temperature is increasing. Now there are a couple of solids that will do this, so be careful when you're figuring this out. Ammonia is made up of all nonmetals, and gases tend to be covalent compounds like this with all nonmetals. So if you see something that looks more like a salt, don't put that one. Put the ammonia, or put whatever looks like a gas. All right, number 5. A saturated solution of potassium nitrate is formed from 100 grams of water. If the saturated solution is cooled from 60 degrees to 20 degrees, how many grams of precipitate are formed? Okay, so we're stating that as it cools, it doesn't form a supersaturated solution. Instead, they precipitate out. Okay. So just treat this carefully. So what we're going to do is first figure out how many grams will fit at 60 degrees. So for potassium nitrate, that's this line right here, KNO3, 90 grams will fit. And for 20 degrees, about 20 grams will fit. So at 60 degrees, 90 fits, 20 fits. Okay, so then what do we do with that information? Well, what's going to happen is that as this cools from 60 to 20, okay, what doesn't fit anymore is going to fall out. So we're just going to subtract the difference to figure out how much doesn't fit anymore. So how much doesn't fit anymore? 70 grams. Or 70 grams of potassium nitrate precipitates out. All right, number 6. 90 grams of potassium nitrate are dissolved in 100 grams of water. Is the solution saturated, unsaturated, or supersaturated? Now it's saying it's dissolved in water. Good. So let's see. Where would that be on this graph? 90. It's all 100 grams of water, so we don't have to worry about that. And 40 degrees. That happens right here. Okay. So we have to see where this dot is in relation to the potassium nitrate line. It is way above this potassium nitrate line. Okay. So it's above it and it's dissolved. If we just put it in there and it didn't say it was dissolved, we just added it, it wouldn't actually make a supersaturated solution. It would make a saturated solution with a bunch of solute at the bottom. So the reason why we're saying this is above the amount and it's supersaturated is because it states in the problem that these 90 grams are dissolved. Okay, if they were just added, then it probably couldn't dissolve. It's above that potassium nitrate line and it says dissolved. All right, that's it for today. See you next time.